All right, we are doing section 5.3, day 1 today. And we're going to start talking about exponential functions. An exponential function is one that can be written in the form of f of x equals a to the x, where a is a positive real number so a is greater than 0 and a is not equal to 1. The domain of f of x is all reals. All right, I do want to talk about why there are these restrictions on a. If a equals 1, then the function would be f of x equals 1 to the x. What is 1 to any power? That's just 1. And that equation simplifies down to be f of x equals 1, which is a horizontal line at 1, and that's just silly to look at. Let's look this way. If a is less than 0, say a equals -2, then we're looking at something like this. F of x is equal to -2 to the x. And we run into problems in that if x is even, this will be a positive number. If x is odd, this value will be negative, so we'll be bouncing all over the place. Plus, how are you going to do something like -2 to the half? That's the square root of -2. That's complex. And so we can't have real numbers and complex numbers mixed. Right now, we are only graphing real numbers. So this is just icky. All right. Now, I do want to compare a linear function versus an exponential function. So I want to look at y equals 3x plus 1 versus y equals 2 to the x. And let's just choose the same x values for each. So let's choose some x values of -2, -1, 0, 1, 2, 3, and 4. And evaluate each of those functions at those 7 values. So putting a -2 in here, that's going to be a -6 plus 1, so -5. -3 plus 1 is -2. 0 is going to be 1. 1 will be 4. 2, oh, are you seeing the pattern here so we don't have to keep plugging back in? Just add 3, yes? So this would be 7, 10, and 13. Let's come over here and look at this. This one's going to be 2 to the -2. That's 1/4. This one's 2 to the -1 is a half. 2 to the 0 is 1. 2 to the first is 2. All right, what's the pattern here? To get from a fourth to a half, and then to a 1, and then to a 2. Sure, it's just multiply by 2. So that's 4, 8, and 16. And what I want you to see here is that in a linear function, we are adding the same amount to the y values for consecutive x values. And what is that amount that we were adding? We were adding 3 here. Oh, look at that. It was the slope in that linear equation. Adding the same amount, which is the slope, to the y values for consecutive x values. So these x values are consecutive numbers. Now let's take a look at what's going on over here in the exponentials. In the exponentials, we're not adding the same amount this time. What are we doing? We're multiplying by the same amount. And what was that same amount for this one? Times by 2, that was the base of that exponent. Okay, so we're multiplying by the same amount to the y values for consecutive x values. Okay. All right. For also, just another way of kind of saying this, for exponential functions, f of x plus 1 divided by f of x is a. For example, if f of x is 8, f of x plus 1 is the next one. That would be 16. 16 divided by 8 is 2, which is the base. 8 divided by the previous term, 4, is the base, 2. All right, now let's graph some exponential functions. And we are just going to start by plotting points. And very nicely, y equals 2 to the x. Look, oh, we had some points generated over here already. So we can just go ahead and plot those points. -2, 1/4. Right there. -1 is at a half. 0, 1. 1, 2. I'm sorry. 2, 4. 3, 8. 2, 3, 4, 5, 6, 7, 8. Okay. We can sketch that in now. All right. That is the general shape of an exponential function. Okay, and kind of a phrase that we like to use to describe exponential functions is that exponential functions get really big really fast. That y value is getting real big, real fast. So at 4, y is 16. At 5, y is 32. All right. Let's look at this page over here. There are some general properties for exponential functions in the form of y equals a to the x. And here are those properties. One of them is that the domain is all reals. The range is y greater than 0. There are no x-intercepts. The y-intercept is 0, 1. This function is increasing, and 1 to 1. Do you remember 1 to 1 has to pass the vertical line test and the horizontal line test? vertical line test and horizontal line test. Okay. These exponential functions are smooth and continuous. And there are 3 nice points. And those nice points are 0, 1, 1, a, and -1, 1 over a. And I missed something in here because I was supposed to have an extra bullet and I missed one. So we're going to have to squeeze one more property in over here on the side. And that is that there is a horizontal asymptote as x goes to -infinity, y is equal to 0. So there is a horizontal asymptote at y equals 0. All right, let's use some of these ideas over here to sketch a graph of y equals 5 to the x. We know the general shape, and we have this idea about 3 nice points. So y equals 5 to the x, one nice point is 0, 1. Got it, right there, 0, 1. 1, a. Well, a is 5. So 1, 5. 2, 3, 4, 5. Right there is 1, 5. Here's 0, 1. And then we have another one, -1, 1 over 5. So 1/5 right there. It's -1, 1/5. We know we have a horizontal asymptote out here. Here's the y-intercept, range is above, so we can sketch this in, connecting these 3 points. Right there. Alright. Now, let's use some transformations to sketch a graph of each of the following exponential functions. So, look at this one, y equals -2 to the x. This negative is outside of the function, and do you remember that that is going to show a reflection over the x-axis? All right. Now with these guys, the exponentials I think are hard to do transformations on, so I always draw the original very lightly, and I am going to do it in pencil. So 2 to the x, -1/2, 0, 1, 1, 2, 2, 4, 3, 8. That's up here somewhere. There's the original. Now let's do the new one, and we're just going to reflect that over the x-axis. And sketch that in. All right, there we go. That's the graph that we want. Now notice, I'll always read pencil, or the real light one, as the kind of the parent graph, and a color one as the final answer. If you don't do the 2 colors, then make one of them significant, or go back and erase out this sketch of y equals 2 to the x. All right, let's look at this one when we put the negative on the inside. And a negative on the inside of the function that's going to be a reflection over the y-axis. original in there. And let's just take that and reflect that over the y-axis. There we go. All right, look at this next one. Y equals 2 to the x plus a 3. This plus 3 out here, what does that do? That shifts our graph up 3. So y equals 2 to the x like this. Let's shift up 3 units. That's going to take our horizontal asymptote at y equals 0 and put it up at y equals 3. And we just graph from there. Just move every point up 3. And there we go. All right. How about this one? Y equals 2 to the x minus 3. That minus 3 is on the inside, so this function will move to the right 3. The horizontal asymptote is not going to change if we shift to the right, just everything goes 3 to the right. There we go. All right, let's look at the next two graphs. And we're going to look at this one. Y equals 1 minus 2 to the x plus 3. Oh boy, threw a lot in this one. Let's just do some rearranging first. What if we write this as y equals negative 2 to the x plus 3 plus a 1. This negative will show a reflection over the x-axis. This plus 3 is going to shift left 3, and this plus 1 will shift up 1. So, when there's all this junk going on, I am going to move my origin. So I'm going to do my shifting first, which is going to be 3 to the left and up 1. So there's like my new origin. And we are going to have an asymptote going right through, a horizontal asymptote going right through, just like before we had a horizontal asymptote going right through the actual origin. Okay, now all we have to, I've taken care of this plus 3, I've taken care of that plus 1. All that we have to do is graph negative 2 to the x, as if that's the origin. Sometimes it helps again still to draw that original. Excuse me. So let's go. Normally from the origin, this function is up 1. But now from the origin, this function is going to go down 1 because of the negative. Normally from the function we would go, or from the origin we would go 1 unit to the right and up 2. So this time, when we go 1 unit to the right, we're going to go down 2. And normally, 2 to the right would send us up 4. So 2 to the right is going to send us down 4. And once you see the pattern, then you can go ahead and sketch this in. And there it is. All right, one last one. Let's look at this. I'm going to do some shifting, rearranging first. So what if we wrote this as y equals 3 to the 1/2 x, and then plus a 2. This plus 2 is going to shift up 2 units. And this half here, because it's on the inside of the function, that is going to be a horizontal stretch. Alright, so here we go. Up 2. New origin sitting right there. And we're going to have a horizontal asymptote at y equals 2. Here's the original. Alright, now we're going to graph as if this is the new origin up here at this hole. So, we're going to have to stretch it out this way. Pull it out. So we're going to affect x coordinates here. So from the origin, when we went 0, we're going to multiply the x coordinate. We're going to double it because it's going to stretch out. That's not going anywhere. So this point actually gets transferred just to right there. Normally from the origin, when we went over 1, we would go up 2. But this time from the new origin, we're going to go over twice as far to do a horizontal stretch. So we're going to go over 2 to go up 2. Normally on the original from the origin, when we went over 2, we go up 4. This time we're going to go over twice as far from the new origin, 1, 2, 3, 4, and still up the same amount. So there. Normally we would go to the left 1 and up a half, but now from the new origin we're going to go to the left twice as far, so left 2 and up a half. Again, if this is really, really bothering you, then by all means plot points. Plot points. It's just much faster to understand the transformations. But if you really get stuck, you're in a bind, then absolutely plot some points. Okay, thank you very much. I hope everything's okay. Use the remaining time to work on whatever homework you need to work on.